Okay, as we generalize our understanding of circuits, we want to be able to deal with circuits where the current and the voltage in the circuits are not constant in time, are not necessarily exponentially changing like they do with RC and RL circuits, but are actually going back and forth in an alternating fashion. To help us develop some tools for dealing with these types of circuits, we're going to introduce a concept called phasors. Phasors are simply graphical representation of time-varying quantities as vectors. That will allow us to generalize our understanding of resistance to a more general form called reactance, and then we can combine the reactance of inductors, capacitors, and the resistance of resistors in a general thing called impedance. That's all we'll cover in this video. Further work using phasors to analyze RL and RLC circuits will be the topic of a different video. Okay, so alternating current is hugely important because it's what comes out of our wall outlets. So any circuit that plugs directly into a wall outlet is by nature an AC circuit. The reason that we have AC current coming out of our wall outlets we'll be able to understand a little bit when we talk about transformers a bit later, but essentially it's for efficiency. AC current can be stepped up to high voltages that can be transmitted efficiently over power lines without a large reduction in power due to resistance in the lines. Okay, so an AC circuit has sinusoidally varying voltages and currents. And so if we write, let's say, a voltage as a sinusoidal variation, we're going to use lowercase v to represent an AC voltage, whereas we were using uppercase v's to represent DC voltages. So this expression right here is a sinusoidal variation, and by convention we'll typically write our sinusoidal variations as a cosine function, such that at t equals 0, if there is no initial phase, our voltage at time 0 will be a maximum that we'll call V naught. So V naught here we call the amplitude of the voltage waveform, and cosine omega t describes how that voltage is varying in time. So omega is the angular frequency. It's 2 pi times the frequency of the oscillation. So if we have, for example, a wall outlet that has an oscillation at 60 hertz, the value of omega that goes into any expressions representing that is 2 pi times 60 hertz. Okay, so likewise we can express an alternating current as having some amplitude I naught and some time variation that we'll also write as cosine omega t plus phi naught. So this term phi naught just is used to represent where on this cosine function we are at times t equals 0. So cosine starts at a maximum. So if t equals 0 happens to be the time at which our function is at a maximum, then phi naught will be 0. But if we wanted to start at t equals 0 at some other point along this waveform, this distance here, measured as an angle, would be phi naught. So in order to represent any of these oscillating functions as a time variation, we need two quantities. We need some amplitude that describes how big the variation is, and then we need some angle. In this case, it's a time-varying angle, but that's the thing that goes into the cosine function that tells us how much the value of the voltage has changed from its maximum value. And so if we need two quantities in order to express this, like r times cosine of an angle, this is just a simple expression for the x-coordinate of a vector in polar coordinates that has a magnitude of r and an angle of theta. Its x-coordinate is just r cosine theta. So looking at this expression for an oscillating voltage, if we recognize that the angle theta is omega t plus phi, And the radius of this this object in polar coordinates is v naught, then what I have is I can represent this time-varying voltage function by a vector written in polar coordinates that has a length of v naught and an angle of omega t plus phi. And because that angle is time dependent, this vector is going to rotate around, tracing out a circle. And as it goes around this circle, the function that we're representing, the voltage, is just the x component of this. So it's the projection onto the x-axis of the tip of our vector. And as the vector goes around, that point is going to go back and forth and back and forth, sinusoidally oscillating, just as our functional form would have us would represent. So we call this quantity a phasor. A phasor is just a vector that's used to represent some time-varying signal. And so the idea is that if we look at the projection of our vector onto the x-axis, then as the phasor rotates around the origin, because its angle that it makes is time-varying, as it rotates around, the x component of that is going to be the amplitude, or the length of the vector, the length of the phasor, times the cosine of the angle that it makes. That's the x component. And this then is our time-varying function. It just turns out to be easier to represent a vector, oftentimes, than it is to represent a time-varying function. So let's look at a little animation of how this works. In the top left, we see this phasor rotating around. And if we drop a line from the end of the phasor down onto the horizontal axis, that length along the x-axis represents the value of our function with respect to time. So as we plot that out, our phasor rotating around at a constant angular frequency will trace out a cosine wave. And when we look at that with the time axis along the x direction, we can see just a traditional cosine wave and the relationship between our time-dependent function and the phasor that we can use to represent it. Okay, so imagine we have a alternating current. We represent that in a circuit diagram by a circuit with some sinusoidal wave. This could be either a alternating current source or an alternating voltage source, depending on whether we label this with a V or with an I. Okay, so that's our circuit diagram for an AC voltage source or an AC current source. Now, one of the things we might want to know is if this is time varying, is there a way to represent sort of the average voltage or the average current? Because that's going to be important for understanding things like how much heat might be generated in a resistor or how much power is delivered to a circuit element. So if we try to take the average of a time varying function, because it's oscillating around a value of 0, the average is going to be 0. So it's not helpful to talk about the average of time varying quantities in terms of what effect they have on a circuit. But if we put an alternating voltage source across a resistor, just because the average voltage is 0, it doesn't mean that the resistor is not going to dissipate any energy as heat. So if what we do is we say, let's calculate how much energy is dissipated by a resistor on average and relate that to the value of the voltage that would be necessary, the DC voltage to be necessary to produce the same amount of heat, we can define that as our effective average voltage that the circuit sees. Okay, so we'll say the average power dissipated by a resistor is going to be V squared over R, or well, the power is V squared over R. But to write this as an average, let's integrate this quantity over some length of time and then divide by that amount of time. That's just what an average is, right? You you add something up for some period of time, and then you average it out. Okay, so as we do that, we can replace our v of t with our expression v naught cosine omega t plus phi, and because it's squared, each of those parameters gets squared. And then as we integrate this quantity, we're integrating over a cosine squared, right? So cosine squared is always positive. It's a square of a number, so it oscillates between a maximum value of 1 and a minimum value of 0. And so its average value over many cycles is exactly 1/2. So this cosine squared is going to average out to 1/2. The v naught squared is a constant and comes outside the integral. And so we end up with v naught squared over 2 times r as our average power dissipated by a resistor with a alternating voltage source. So we'd like to relate this to the voltage necessary in a DC circuit to dissipate the same amount of power. And so we relate that. So we relate that v naught squared over 2r to v squared over r that we'd have in a DC circuit. And the voltage that we plug in to our DC circuit, we're going to call some sort of average. In this case, it's an RMS. I'll describe what RMS means in a minute, but V sub RMS is the equivalent DC voltage that will give us the same dissipated power that we have on average for our AC circuit. So solving this for VRMS gives us V naught over square root of 2. So VRMS is some sort of average voltage that's a little bit less than the peak voltage V naught. So RMS stands for root mean square. It's a type of average where instead of just averaging a quantity directly, you first square it so that it's always positive. And that way when you average it out, you're not averaging out to 0, but rather you're averaging out, you're calculating not the average value of the voltage, but the average sort of distance away from 0 that the voltage is, regardless of whether it's positive or negative. So this is an example of power in a resistor. More generally, if we want to talk about power in AC circuits, we can say that the power is current times voltage, and the current is also going to be sinusoidal. So we will write the current as I naught cosine omega t plus phi. And now, together with that current and our definition of the voltage, and I'm allowing some phase difference phi between the voltage and the current. So maybe the voltage is a sine wave and the current is a cosine wave or something like this. That's what that extra phi naught means. But we can then say the power as a function of time is just current times voltage. That's regardless of whether that's the power in a resistor or a capacitor or an inductor or anything else. That's a completely general relationship. We're using this form of power as opposed to V squared over R or I squared over I squared R, because we're not assuming that this is the power in a resistor. It's just the power dissipated by some current flowing across some voltage difference. So if we want to figure out the average power, or even if we just want to multiply these quantities together, we're multiplying two cosines together. So we're going to use the trig relationship that says cosine A cosine B is 1/2 cosine of the difference plus cosine of the sum. So that allows us to write this power expression down here as 1/2, that comes from the trig relationship, I naught times V naught, that comes from the amplitudes of the two time varying functions that I'm multiplying together. And then I get this expression that has the sum and difference of the cosines. So if I take the difference of these two arguments, the omega t plus phi naught cancels out, and I just get this cosine of phi, where phi was the difference in phase between the current and the voltage, if there is one. And then this other term over here, which is the cosine of the sum of the two arguments, because this is varying at twice the frequency, on average, this is going to average out to 0. Okay, so if I'm calculating an average power, this term on the left is non-zero, the term on the right averages out to 0. So I just have the term on the left contributing to the average power. And what I see is the average power is 1/2 of the peak power. So I naught times V naught. I naught is the peak current, V naught is the peak voltage. And so the peak power would be I naught times V naught, but because the power is oscillating between 0 and this value, the average is 1/2. Now there's also this cosine phi term, which tells us there's only power being dissipated if the current and voltage are in phase, meaning if if they either have the same phase, so they're both varying sinusoidally, or at least they're not 90 degrees out of phase. If phi is equal to 90 degrees, then the power dissipated is 0. Well, we can also use the fact that the RMS current is 1 over square root of 2 I naught, and the RMS voltage is 1 over square root of 2 V naught, to say that 1/2 I naught V naught can also be written as IRMS VRMS. So by keeping track of the RMS values of current and voltage, we can use them in the same way that we would use DC values to calculate power. That's one of the reasons that it's useful to talk about RMS values. The easiest circuits to analyze are ones where we just have resistance causing the current and voltage to differ by Ohm's law. And if that's the case, we'll see that phi naught is equal to 0. And if phi naught is equal to 0, this cosine is 1, and we have a very simple expression for the average power. It's just the RMS value of current times the RMS value of voltage. Okay, if we have a current in our circuit that's sinusoidal and represented by I naught cosine omega t plus phi, that's saying that there's a certain amplitude and there's a sinusoidal variation. If that current flows across a resistor, we know that V equals IR, and that's true whether we're dealing with DC circuits or AC circuits. So I can just multiply this expression for the current times R and get an expression for the voltage, and that's right here. So if I want to represent these voltages and currents as phasors, at some moment in time, let's say my phasor has rotated so that it's pointing at 45 degrees. If this magenta arrow represents the phasor for the current, then the phasor for the voltage should point in the same direction and should have a length that depends on the amount of resistance. The bigger R is, the bigger that voltage will be, and so the longer that phasor will be. Let's consider an inductor. We want to come up with something that's sort of analogous to resistance in an inductor that will tell us for a given voltage how much current is there. And that quantity we're going to call the reactance of the inductor. Okay, so let's use our definition for the voltage across an inductor is L times di dt. And we're going to assume that the current is sinusoidally varying. That's an AC current. And so we're starting with that just like we did for the resistor on the previous page. Now we can calculate the voltage from plugging this in for the current. So we have to take the time derivative of this. Our I naught, that's the amplitude, that's a constant. When we take the time derivative of cosine, we get sine. And then using the chain rule, we have to take the time derivative of the argument here. And so the time derivative of that is omega. That gives us this omega here. And then we still have the L from our definition. And this minus sign comes from the derivative of cosine being minus sine. So we get an expression for the voltage as a function of time, which is written as a sine wave. Our current was written as a cosine wave. So sines and cosines are very similar, right? They're both oscillations. If we plot them versus time, they both go up and down, but they're shifted by 90 degrees. So we can use the fact that our minus sine is equal to cosine plus 90 degrees. So we can replace the minus and the sine with cosine of our original function plus 90 degrees. And in doing that, we now have an expression that we can write as a phasor and compare it to the current written as a phasor. So if our current at some moment in time is represented by a phasor with a certain length, I'll draw it in magenta here on my phasor diagram, then the voltage is going to have a particular length for its phasor corresponding to the height of the voltage on my voltage versus time graph. But because of that 90-degree phase shift, the voltage is 90 degrees ahead of the phasor for current. So because phasors are rotating counterclockwise, that's the direction we measure angles in polar coordinates, I have to go an additional 90 degrees to be able to draw my voltage phasor. And so it's a phasor that's pointing up and to the left that makes a 90-degree angle with respect to the current phasor. So we see that while the current might have a positive value, its projection on the x-axis is positive, and decreasing as the phasor rotates, the phasor for the voltage tells us that the voltage is currently negative and is going to be increasing at this moment in time. So we can see that on this graph over here of voltage and current as a function of time. There's this 90-degree lead for the voltage relative to the current. We can also see it on our phasor diagram here. If we do this, we can write the ratio of the length of these two phasors. So the magenta phasor has a length of I naught, the blue phasor has a length of V naught, and the ratio of those two things, V naught over I naught, we were calling that resistance when the phasors were in phase, and now we'll call it something more general. We'll call that the reactance. So the reactance is the ratio of voltage to current phasors when they're not in phase. And so the reactance of this particular example for an inductor, I can work that out. The value for V naught is just this, I naught omega L. And when I divide that by I naught, the I naughts cancel, and I find the reactance is omega L, written up here. So an inductor, we say, has a reactance of omega L, and reactance is a little bit like resistance. We say V equals IR for resistance, and now we can generalize that to say the magnitude of an alternating current or an alternating voltage is related to the magnitude of the alternating current times reactance. Okay, so it obeys a very similar expression. Let's see if we can figure out the reactance of a capacitor in the same way. So again, we're going to start with an expression for current that's sinusoidally varying and a definition of the voltage across the capacitor. The voltage across the capacitor is just Q over C, and the charge on a capacitor is just the current integrated with respect to time. So if it starts discharged and there's current flowing onto it, that current times however long it flows is how much charge we end up with. So we can integrate from t equals 0 to some time t, the current flowing onto a capacitor divided by the capacitance. And of course, we'll just use this expression that we have for the alternating current. So we'll end up integrating a cosine, and the integral of cosine is sine. So we end up with sine omega t plus phi. And again, from the chain rule, because we have an omega out front, we're going to end up with a 1 over omega when we do the integral. So you can check this. If you take this expression that we have for this integral, if you take the derivative of this, you should get back to our expression for the current. But this expression here then becomes the expression for the voltage of the voltage on a capacitor when I have this AC current that I've defined. So again, this voltage is a sine wave where the current was a cosine wave. So I'm going to use the fact that sine of phi is equal to cosine of phi minus 90 degrees to write this as a cosine. So I'm going to write it as a cosine of my original argument minus 90 degrees. And what that does is it lets me say that if the current is again a phasor at one particular time, I'll draw it sort of up and to the right at 45 degrees, but that's just at some arbitrary time where it's rotated that far. Then the voltage is going to have some amplitude that is given by the factor in front of this cosine wave. And then this 90-degree phase lag tells me that the phasor for the voltage must be 90 degrees behind that of the current. And so since phasors rotate counterclockwise in time, it must be 90 degrees further clockwise to represent that voltage across the capacitor. And now I want to say that the reactance of this capacitor is the ratio of the peak voltage to the peak current. And that peak voltage I've worked out is I naught over omega c. And so when I divide that by I naught, I get that the reactance is 1 over omega c. So we can generalize this idea of resistance and reactance being the ratio of two voltages, and we'll call the impedance the ratio of the maximum voltage to the maximum current. And we can use that to represent resistances. So if we have a resistor, we know that V equals IR, and so the impedance is R. If we have an inductor, we know that the relationship looks like Ohm's law, but it's V equals IX, where X is the reactance, omega L that we just saw. And so that omega L, or if we have a capacitor, the reactance of 1 over omega C, these quantities, resistance, omega L, or 1 over omega C, are all called impedances. Okay, so reactances are impedances that lead or lag by 90 degrees, and resistance is an impedance that's in phase, meaning the voltage is in phase with the current. But in general, impedance is the term that we use to represent the ratio of maximum voltage to maximum current in a circuit.